Hi, in this video, I'm going to go over the analysis of the buck converter. Now, the buck converter is a very fundamental step-down DC-DC converter. This means that it's a circuit that converts an input DC voltage to a smaller DC voltage level at the output. Now, more specifically, the buck converter is a DC-DC converter that's classified as switch mode. Now, to motivate why we use switch mode power converters like the buck converter, I'm going to start by explaining what the linear voltage regulator does. Now, the linear voltage regulator is a DC-DC converter, but it's not switch mode. Now, the circuit for the linear voltage regulator is quite simple. We have a voltage source Vs, and then we have a variable resistor, let's call it R var. And then we have a load resistor, RL. And the output voltage, VO, is taken across the load resistor, RL. Now, how this circuit is actually implemented, particularly the variable resistor, is that we have some type of a transistor, such as a BJT, and this BJT has an effective resistance in which by varying the base current IB into this BJT, then we can vary the effective resistance. So this is in essence how we would implement this circuit, particularly R var. Now, this circuit it lends itself to very basic circuit analysis. So we can say the output voltage is just given by a resistive divider. So VO is equal to RL over RL plus R var times the source voltage Vs. Now, the main drawback of the linear voltage regulator is that it has very low efficiency. And what I mean by that is let's take a look at the current. So the current is IL. The load current is the same throughout this whole circuit because everything's in series. And the input power is given by voltage times current. So the voltage is Vs and the current is IL. So this is the power that the source voltage Vs is delivering to the rest of the circuit. Now the output power is given by the voltage is VO and the current is IL. So therefore, the efficiency by definition is the output power over the input power. And then substituting these expressions, we get VO times IL over Vs times IL. Because the currents are the same, we get that the efficiency of the circuit is equal to the output voltage over the source voltage. Now, this is actually a big drawback in terms of the efficiency because, for example, say we chose the resistor values such that we converted 5 volts down to 3 volts. So Vs is 5 and VO is 3. Then the efficiency is equal to 3 over 5, which is equal to 60%. So this means 40% of the power is wasted away in this variable resistor and not actually delivered to the load resistor. Moreover, say we had a source voltage instead of 10 volts and we converted that down to 3 volts. Then our efficiency is equal to 3 over 10, which is 30%. So in this case, if we have a higher step down ratio of 10 to 3, that means a whopping 70% of the energy of the power is wasted away in R var and not actually delivered to our desired load resistor. So this is the main drawback of linear voltage regulators. And this motivates our study of switch mode power converters. in which the buck converter is a very fundamental topology. So I'm going to show a very basic example now of a switching converter. And actually, it's the same topology as this circuit here, except we're going to operate it differently. So particularly what we're going to do is we're going to, instead of operating the transistor in its region where it operates as a linear resistor, we're going to turn on and off this transistor completely. This means the way that we operate the transistor is that we turn it on and off completely, just as an ideal switch. So in this case, we're just turning on and off an ideal switch, and we still have the load resistor like this as before. Now, what we want to do is we want to turn on this switch during the interval T on, and then we're going to turn off the switch during the interval T off. So when the switch is on, during the interval T on, let's call this T on, then our output voltage, which we desire, let's call the output voltage VO. The output voltage during this time interval, is simply equal to Vs, because Vs is shorted to VO when the switch is on. So in this case, we have VO equals Vs. Now, during T off, let's call this interval T off, then what we're going to see is that the output voltage has no current. This circuit has no current flowing through it, so there's no voltage drop across RL, so VO is just equal to 0. So in this case, we have VO is just equal to 0 during the off interval. And what we're going to do is we're going to operate this circuit periodically, so then this whole cycle just repeats itself continuously, and so on. So this, for example, would be T plus T on, and then this would be 2T, and so on. Now, what we see here is actually the output voltage is a pulsed waveform, but it has a lower DC component. So by the Fourier series, we know that the output DC component, so we're going to put these brackets around VO, meaning that we're looking for the DC component of this pulsed waveform, is equal to capital VO, and then we're going to do 1 over the period and then integrate the pulsed waveform over this period. So this is the definition of the DC component when we decompose this waveform with its Fourier series. And just simplifying this integral, because it's 0 during the T off period, we have 0 times T on, 0 to T on of Vs dt. So what this is going to give us is we're going to have 1 over T times Vs times T on. Now we're going to use another definition here, and that is the duty cycle D is equal to T on over T. So this is simply the fraction of the period in which the switch is turned on, and that fraction is defined as the duty cycle D. So then T on is, so that means that T on equals dt. So we have that this T on is also equal to dt. Therefore, simplifying this, we have 1 over T times Vs times dt. The T's cancel out, and we're simply left with D times Vs. So therefore, the DC component we have found, and it's this value of D is always between 1 and 0. And what that means is the DC component is going to be some value like this. So this is VO, VO equals D times Vs. So we have found that we can use this so-called DC chopper to take a DC voltage and then chop it up into pieces um, with duty cycle D and get a DC component at the output that is smaller. And moreover, because this switch is ideal, when the switch is open, we have no current flowing through it. And when the switch is closed, there's no voltage across it. The voltage is 0. So if we have the power consumed by the switch is equal to, let's say the power consumed by the switch is equal to the current through the switch times the voltage across the switch. One of these values, either the current through the switch or the voltage across the switch, is always 0. So therefore, in this case, the power consumed by the switch is always 0. So in this switch converter, we can see that actually the energy efficiency is 100%. And this is because the way we're operating the switch allows no power to be consumed by the switch. And therefore, we get very high efficiency. However, there is a problem with this simple circuit. Although some applications can take this output voltage VO to be pulsed, in most applications, we would prefer that the output is purely DC. So how we would um, obtain a circuit in which the output is purely DC and not this pulsed waveform as shown here is that we want to add a low pass filter to this circuit. So a very basic low pass filter is the LC filter. So we can add across this switch an LC filter. And the goal of the LC filter is to only retain the DC component. Now, because when the switch is turned off in this state, we still need current to flow through this inductor. So it turns out we're going to also need a diode here to give a path for the inductor current to flow when this switch is off. Now, this topology is the buck converter. So let's label some of the voltages and currents in this circuit. So across the diode, we have Vx, and then across the inductor, we have VL, and the current going through the inductor is IL, the current through the capacitor is IC, and the current through the resistor is IR. Now, basically, for this analysis, we had taken our circuit from before and then inserted a low pass filter after it. So for our Vx waveform, we simply have when the switch is closed during the DT interval. So during the DT interval, we have the switch is closed, the diode is open. So that means Vx just equals Vs. So we're drawing the Vx waveform during the dt interval in which the switch is closed. We have Vx equals Vs. Now, during the so-called d prime interval, the switch is now opened and then the diode is turned on. and conducting the current through the inductor. So that means that during this period, because the diode is on, it's just a short circuit, and Vx is shorted out, so it's equal to 0 during the d prime t interval. So this cycle just repeats periodically as we operate the circuit in steady state. This is our time axis. And essentially what we have here is, as we analyzed before, an average DC value of Vs times the duty cycle D. And D is the fraction of the period in which the switch is turned on. So with the low pass filter, we simply filter out all the other frequencies, and we simply retain the fact that V out is equal to the duty cycle times the source voltage. Now we can also view this in the frequency domain. So we have this pulsed waveform, right, for Vx. In the frequency domain, we can decompose this pulsed rectangular waveform into its frequency components. So now this is the frequency axis. And at DC, which is where the frequency equals 0, we have the DC component, right, which is D times Vs. And then because we're operating in this periodic steady state where we're repeating the turning on and turning off the switch periodically, we have the switching frequency, FSW, equals 1 over the period. And because our period is 1 over t, we're going to get these harmonics of the switching frequency. So this is basically the Fourier decomposition of this rectangular waveform for Vx. So the main thing is that this is the frequency domain representation of Vx. And then we have this low pass filter given by the inductor and the capacitor. And all that it's going to do is it's going to give us a cutoff frequency like this. So this is given by our LC low pass. And then at the output, VO is just going to be our DC component, D times Vs. So this is the frequency domain way of looking at things. So that is one way of looking at the operation of a buck converter. Now I'm going to go through another way of analyzing the buck converter, and that's by specifically examining the inductor voltage. And this analysis method that I'm going to show is going to be very useful later on for analyzing other switch mode converters. So there's several assumptions that I'm going to state that are basically essential to the analysis. And as I mentioned before, the first assumption we're making is that the converter is operating in steady state. This means that the circuit has finished its startup process and it's running in a repeating cycle. And actually, what that means is we're actually going to see that the inductor voltage, the average inductor voltage, is equal to 0. And why that is the case is because of this. So we know the inductor characteristic equation. The voltage across the inductor is equal to L times DIL dt. Now, if we divide both sides by L and then integrate, so let's divide both sides by L. And then we're going to integrate both sides. dt. This is going to give us 1 over L integral from 0 to t, because we're taking the integral over a period, VL t dt is equal to IL of t minus IL of 0. However, because our assumption is that we are in steady state, the current through the inductor at the start of the period is exactly the same as the current through the inductor at the end of the period. So that means IL of t equals IL of 0, and therefore this equals 0. What this implies is that the integral of the voltage across the inductor during one cycle is equal to 0. So this means that if we divide both sides by 1 over t, it's still equal to 0, but this is just equal to our average inductor voltage over one period. So therefore, this analysis shown here demonstrates why in all switch mode power converters, we have that the inductor voltage across one period is equal to 0. This is also called inductor volt second balance. So by the same token, we'll find that the average capacitor current across one period is equal to 0. We can do the same exact analysis, but instead of the inductor characteristic equation, we use the capacitor characteristic equation, which is I equals L dV dt. So this principle is also very important, and it's called the capacitor charge balance. These two principles are very essential for analyzing switch mode power converters. So this is our first assumption, steady state, which gives us the inductor volt second balance and the capacitor charge balance statements. So the next assumption that we make is the small ripple approximation. Small ripple approximation. So this means that we assume that in our buck converter, this output capacitor C is large enough that we assume that any output voltage ripple across the load resistor is negligible compared to the DC voltage. So that just means that the output voltage, V out, is equal to a constant value. Now, this is an approximation that we're making. We will relax this approximation later on when we want to really analyze what the ripple is at the output. But for now, we're going to assume this approximation that the output voltage is just purely a constant DC value holds. So the next assumption we're going to make in this analysis is that all the components are ideal components. What this means is we're going to do a basic analysis where we ignore losses. That means that we assume our transistor is ideal. It's just a switch, an ideal switch, as well as our diode is just an ideal switch. So this ultimately gives us that the input power is equal to the output power. And what that means is we don't have any losses, and therefore we have 100% efficiency. As we'll later see in more advanced analyses, we will add in these lossy components to examine the efficiency more accurately. Okay, so let's begin the analysis for the buck converter in the continuous induction mode. So this is one more term that is important in our analysis. And what this means is we're analyzing the buck converter in the case where the inductor current is always positive. This means that the inductor current never falls to zero. Now, later on, we will also analyze the buck converter in the discontinuous conduction mode. And in that case, the inductor current can fall to zero. But for now, we are assuming in this analysis that the inductor current is always positive. So let's begin our analysis with these assumptions in mind. And we will start by looking at the buck converter when the switch is turned on and when the switch is turned off. So as you can see in this diagram, we're just going to break this circuit into two states. First state is during the DT interval, where the switch is turned on, and then the D prime T interval, in which the switch is turned off. So let's draw that out. DT interval, the switch is on. So we have the source voltage, the switch is turned on. Now the diode, because the switch is turned on, we have that the diode is going to be turned off. And we have the inductor, the capacitor, and the load resistor. So let's just label this as VL. And then we have this is Vx. And then this is V out. Now, in this analysis, we want to examine the inductor voltage. So during the DT interval, the inductor voltage, VL, we can see is equal to the source voltage minus the output voltage. Because this node is just Vs, and then this node is V out. Now, let's examine the circuit during the D prime T interval, in which the switch is off. Now, in this interval, the switch is an open circuit, but you can see that in this DT interval, we have the current flowing through the inductor like this so. And we know that we can't suddenly stop the flow of current through an inductor because bad things will happen. We'll get huge voltage spikes in the circuit. So the current through the inductor is always continuous. So therefore, we need the diode to provide a path for the inductor current to flow. So in this case, the diode's going to short, um, providing that path that we need for the inductor. So in this case, we have VL and Vx. So we can see that in this case, the inductor current is going to flow like this. Okay, so in this method of analysis, we examine the inductor voltage. And in this interval, we have the inductor voltage is equal to, so this node is 0, and then this node is VO. So the inductor voltage is negative VO. Now, remember that we derived that in steady state, in periodic steady state, the inductor average voltage is equal to 0. So if we take the average inductor voltage, we have during the dt interval, we have Vs minus Vo. And then in the d prime interval, we have negative Vo. So if we simplify this expression, we get d times Vs minus d times Vo minus d prime times Vo. Now, d and d prime, d plus d prime is just equal to 1. So we get d times Vs minus 1 times Vo, and this whole thing equals 0 by the inductor volt-second balance principle. And by examining the inductor voltage, we now find that Vo just equals d times Vs. So we've arrived at the same voltage conversion ratio that we found before using our original analysis. And in doing so, we have examined how to analyze the circuit in the dt and d prime t interval, looking at the inductor voltage. So the next step for us is to figure out what the inductor current waveform looks like, as well as what the capacitor current waveform looks like. So let's start by drawing the waveform for the inductor voltage VL. So we know during the dt interval that we have VL equals Vs minus Vo. And then for the d prime t interval, we found that VL equals negative Vo. So note that in this interval, dt interval, in this interval, we have a positive voltage across the inductor, and then d prime t interval, we have a negative voltage across the inductor. So what this means is that during the dt interval, because the inductor voltage is positive, we have that this current through the inductor is overall increasing. So we have IL is going up. Now, because in this d prime t interval, the voltage across the inductor is negative, that means that the current through the inductor is going down. And we know this because of the characteristic equation that VL equals L dIL dt. So if this is positive, then we know that the change in inductor current is positive, which means that the inductor current is increasing. And likewise, if the VL is negative, then we know that the inductor current is decreasing. So what this means is during the dt interval, we have that VL equals Vs minus Vo equals L dIL dt. And we know that dIL we can express as delta IL over the time interval dt. And this is because during this entire interval, the inductor voltage is a constant value, so we know that the change in inductor current is linear. So if we solve for the change in inductor current, we have that change in IL over dt equals Vs minus Vo over L. Likewise, for the d prime t interval, we have change in IL over d prime t equals negative Vo over L. So what this means for our waveform for the inductor current is that we have during the dt interval, the inductor current is increasing. with slope, positive slope, Vs minus Vo over L. And then during the d prime t interval, I should draw that so that the axes are aligned. We have that the inductor current is decreasing with the negative slope, negative Vo over L. And we see that the inductor current at the beginning of the period equals the inductor current at the end of the period because we're assuming we're operating in periodic steady state. So the cycle will repeat as so. So we found that the inductor current waveform, and we want to solve specifically for this value of the minimum inductor current as well as the maximum inductor current. So from this equation, we can derive that the change in inductor current IL over the dt interval is equal to Vs minus Vo over L times dt. So this is, in essence, in the dt interval, we have that the inductor current increases by this amount. Now, what is the average inductor current? Let's go back to our circuit here. So in this buck converter, we now call upon our principle that the average capacitor current is equal to 0 in periodic steady state. So this means that we have here that IL equals IC plus IR. Now, if we take the average of both sides, we get the average inductor current equals the average capacitor current plus the average load resistor current. Now, in periodic steady state, we had derived before that the average capacitor current is 0. This just means that over one period, there's no new charge being accumulated on the capacitor because we're in steady state. So therefore, the average inductor current is just equal to the average current in the load resistor. So in the average case, this inductor current flows directly to the output. Now, the average load current is equal to the output voltage over the load resistance R. So therefore, we have found the average inductor current as VO over R. So we can say that this average inductor current, IL, equals VO over R. So therefore, if we want to find the maximum inductor current, that just equals the average inductor current plus delta IL over 2. Because you can see, we can just break down change in IL into two equivalent parts. So if we simplify this, we have that substituting in the inductor current average, we get equals VO over R plus delta IL. So delta IL we had found was Vs minus Vo over L times dt. And then because we just want half of that delta, we add a factor of 2 in the denominator. Now there's another way we can express delta IL, and that's using the d prime t interval slope. So we have delta IL. In this case, delta IL is also equal to, so this slope, if we take the magnitude of it, times the time interval, which is 1 minus dt. This is another way to express delta IL. So we can either express it in terms of the slope in the dt interval or the slope in terms of the d prime t interval. So these two expressions are completely equal. So we can also write that I max is V out over R plus delta IL expressed using the d prime t interval as VO times 1 minus dt over 2L. So these are equivalent expressions, and I'm going to box this term as the expression we found for I max. Now, the minimum inductor current follows easily from this. It just equals the average inductor current minus delta IL over 2. So therefore, we have same expression except a minus sign here. And we can just maybe factor out the output voltage just to simplify things a little bit more. And we have the expression here. And one more thing, the t, which is the period, can just be expressed as the switching, as 1 over the switching frequency f. So this is our expression for I min. Now, in this analysis, we have assumed that the inductor current is always positive. That means that it never reaches 0 in our operation of the buck converter. So to ensure the inductor current is positive, we look at the boundary case between the continuous current mode and the discontinuous current mode. So this happens where the minimum inductor current, I min, equals 0. So if this is the case in which we use the minimum inductance, L min, L min will give us the case in which the minimum inductor current goes to 0. So in this case, we have substituting the expression, the value of the inductance will be L min. So this is the minimum inductance we have to use to ensure we stay in the continuous current mode. So because this equals 0, we can divide V out on both sides. Then we just get 1 over R equals 1 minus D 2L min times F. So this just simplifies. If we isolate L min, we get that the minimum inductance needed to be in the continuous mode is 1 minus D times R over 2F. And this is for continuous current operation. Now, when we design the buck converter, another important design criteria we look for is the peak-to-peak variation in the inductor current. And we had found that previously based off of our analysis of the dt and d prime t intervals, that the change in inductor current is equal to Vs minus Vo over L times dt. And that also equals, if we simplify t to be 1 over f, we have Vs minus Vo over Lf times d. And this also equals, if we substitute Vo equals Vs times d, that Vs equals VO over D. So then we get that this expression equals VO times 1 minus D over LF. So if we move the inductor to a side by itself, we get L equals Vs minus VO over delta IL F times D, and that also equals VO times 1 minus D delta IL F. So if we want to design for a certain inductor current variation, and we've also selected our switching frequency and desired duty cycle, we can then determine the value of the inductor based on this equation. So there's one more thing, is that because we're assuming that the components are ideal, we have the input power, which is P in, is equal to the output power P out. Now the input power is equal to the voltage source Vs times the input current Is is equal to the output voltage VO times the output current IO. Now if we divide both sides by VO, we get Vs over VO. Divide both sides by Is, we get IO over Is. So if we note these relationships, this is actually very similar to the relationship for an AC transformer. So therefore, we can view the buck converter as being essentially equivalent to a DC transformer. So the next step for analysis is we want to examine the output voltage ripple. So we want to study the output voltage ripple. Now, if we examine the filter, we have the LC filter and the load resistor. Now, we have the inductor current here, IL, and then the capacitor's current and the load current IR. Now, the capacitor current by KCL is IL minus IR. Now, we know that the average capacitor current, IC, must be equal to 0. This is because we're operating in periodic steady state, and we cannot accumulate new charge on the capacitor over one period. So from this analysis, we had found that the average inductor current is equal to the average load resistor current. Now, what this implies is we have all of the DC current of IL flowing through the load resistor. So as before, we had found that all of this DC inductor current goes through the load resistor. Now, what about this ripple current through the inductor? Where does the ripple current go? So if we analyze this circuit, we know that the impedance of the capacitor is equal to 1 over j omega c. Now, 1 over j omega c is the impedance of the capacitor. Now, we see at DC, which is omega equals 0, DC, the impedance of the capacitor approaches infinite. So that's why all of the DC current flows through the load resistor, because at DC, the capacitor presents an infinite impedance. Now, what about at the switching frequency, where omega equals 2 pi f? This is the switching frequency. In this case, we have ZC equals 1 over J 2 pi f, switching frequency times the capacitance. Now, if this switch frequency is large enough, then that means this impedance is small. So if we design this output filter capacitor C to be large enough, essentially at the switching frequency f, we're going to get the impedance of the capacitor to be small. If this impedance of the capacitor is small enough, the current wants to flow through the path of least resistance. So in that case, the ripple current, which is at the switching frequency and its harmonics, will choose to go through the capacitor path. So therefore, in our output voltage ripple calculation, we're going to assume that all of the inductor current ripple goes through the capacitor. So if we draw out the capacitor current, it's going to be equal to the ripple component of the inductor current. So it's going to look like this. Now, how do we find an expression for the output voltage ripple? So the key is that we want to examine the charge on the capacitor. So we know that for a capacitor, the charge stored on the capacitor is equal to the capacitance times the voltage across the capacitor, which is VO. So we can also express the change in charge on a capacitor is equal to the capacitance times the change in VO. And the change in VO is the peak-to-peak voltage ripple that we're looking for. So if we isolate change in VO, we get change in VO equals the change in capacitor charge over the capacitance C. So the change in charge is the area of the triangle above the time axis, which is this area. This is the change in the capacitor charge. And we can solve for this area, change in Q, because we know this is symmetrical to this area that's negative. We know that this is just equal to half T. And then this value we know is delta IL over 2, because we know that all of the inductor current ripple flows through the capacitor. At least that's an assumption we're making here. So by the area of a triangle formula, we just have half times base times height. So this gives us that the change in capacitor charge is equal to the period times the delta IL over 2 to the third, which is 8. So now we can substitute this expression in for delta Q. So therefore we get that delta V out, the output voltage ripple, is equal to P delta IL over 8C. So with this expression, we can further substitute in the value for delta IL, which we had found before was equal to VO times 1 minus DT. over L. So the two T's we can also express as 1 over F squared. So then we get VO times 1 minus D over 8 LC times the switching frequency squared. So delta VO, once again, is the peak-to-peak output voltage ripple. And we often want to express the output voltage ripple as a fraction of the total DC output voltage. So this figure of merit is equal to 1 minus D over 8 LC F squared. And this is an important expression for our buck converter. Now, it's often useful if we want to, in our design, determine what we want the capacitance to be to get a specified voltage ripple. We can isolate C, the capacitance, and divide by the ripple voltage ratio, and we get 1 minus D over 8L delta VO over VO times the switching frequency squared. So these two expressions are equivalent, but this expression is helpful for choosing the capacitance value to give us a desired peak-to-peak output voltage ripple ratio. So the output voltage waveform won't be purely DC. It will look something like this waveform. So there will be the average DC value, which is V out as desired, but we're going to see this ripple at the output. And this peak-to-peak value is equal to delta VO. Now, there is one more thing to consider, and that's actually that the capacitor also has an equivalent series resistor. So capacitors that you use to actually design in your converter aren't ideal. So actually, a model that you'll use in design is actually equivalent series resistance, RC, of the capacitor. So this is all in parallel with the load resistor RL, and we have the inductor here. Now, what this means is that we're going to get additional ripple voltage component from this ESR of the capacitor. In this term, we can express as the output voltage ripple due to the ESR. And that's going to be equal to, because we know the current here is IC, which is equal to the inductor current ripple, we will get that the voltage drop across this ESR is equal to delta IC times the ESR value. And delta IC is equivalent to the inductor current ripple. So this is an expression we have for the additional output voltage ripple component due to the ESR. Now, as a worst case condition, you can assume that the total peak to peak ripple voltage just adds up with the ripple due to the pure capacitance C. And that would give you a worst case condition of delta VO due to just the capacitance C plus the ripple voltage due to the ESR. Now, the peaks of the capacitor, pure capacitor ripple, and the peak of the ESR ripple, they won't coincide. So the total output voltage ripple will be less than this. So this is a worst case. However, depending on the design, sometimes the ripple voltage due to the ESR is much larger than the ripple voltage due to the pure capacitance. So that's just something to keep in mind during the design. You will be able to find some information on the ESR from the manufacturer of the capacitor. So another design consideration for the buck converter is synchronous rectification. Synchronous rectification is when we use another MOSFET instead of the diode for that low side switch. So the circuit would look like this. So we still have that MOSFET as our high side switch, but instead of the diode for our low side switch here, we use another MOSFET. And the advantage of this topology of using a second MOSFET instead of the diode is that we can get a much lower voltage drop across this MOSFET S2 compared to a Schottky diode. So typically for these applications, we will use a Schottky diode, especially for low voltage, high current applications. For example, power supplies for CPUs. In this case, the low side switch for a Schottky diode would have a voltage drop when it's on of zero point 0.3 to zero point 0.4 volts. Now, using a MOSFET for S2, we can get a much lower voltage drop. This is because the MOSFET is modeled as an equivalent resistance RDS on, and this RDS on can be very low in the single digit milliohm range. So the voltage drop will be lower across the MOSFET S2 as compared to a Schottky diode, and this will give us higher circuit efficiency. Now, it is important that we actually have a diode here placed in parallel with the MOSFET S2. This could either be the MOSFET's intrinsic body diode, or it might be an extra diode, like a Schottky diode for its switching performance. But the idea is that we have to operate the switches S1 and S2 with a dead time because we're turning these switches on and the other one off. We cannot have the switches turn on at the same time because if these switches are turned on at the same time using our um, control circuitry and timing circuitry, then that would mean we would short out VS, and that would result in a huge current in our circuit and lead to very bad efficiency. So we still need this diode here in the case where during the dead time, there's still a path for the inductor current IL. So this synchronous rectification is very important for low voltage, high current applications. And it's another design consideration to make when designing a buck converter. So most buck converters are designed to be operated in continuous current mode. And we can choose the switching frequency and the inductance to give us that continuous current using the equations we had derived before. Um, and we can note from the equations that as we increase our switching frequency, we can actually reduce the inductor value as well as the capacitance value to have the same output ripple. So the inductor and capacitor values both decrease when we increase the switching frequency. And this is beneficial to reduce the size of these passive components with higher switching frequencies. However, with higher switching frequencies, we also get increased power loss in the switches. And that means that with more power loss, more heat is produced. So therefore, we might need a larger heat sink, which then offsets our reduction in size of the inductor and capacitor. So that's one trade-off to keep in mind as well during the design process of the buck converter. So as I said before, most buck converters are operated in continuous current, as it's desirable. But it's also possible to operate the buck converter in the discontinuous current mode. So I'm going to go ahead and analyze the buck converter for the discontinuous induction mode. So in this case, we have that the inductor current, by definition in discontinuous mode, reaches zero before the end of the period. So that means the inductor current will look something like this. So if this is dt and we have t here, the inductor current will rise during the dt interval, and then at some point before the end of the period, it will fall to zero. And once again, we have periodic steady state operation, so it's going to repeat every cycle. So this interval, let's call d1t. And correspondingly, the voltage across the inductor will look like the following. So we have during the dt interval, d1t and t. So during the dt interval, the inductor voltage will be Vs minus Vo. And then during the d1t interval, we're going to have the inductor voltage be negative Vo. And then during this final interval here, the inductor voltage is just zero. This is d1t. So we still require that the inductor voltage average be equal to zero. And this is once again because we're still operating in periodic steady state. The inductor current at the beginning of the cycle is zero, and it's still zero at the end of the cycle. So therefore, we must have the average inductor voltage, VL, is equal to zero. And we can take the average during the D interval. We have D times Vs minus Vo, plus during the D1 interval, we have negative Vo. And if we simplify this to find the voltage conversion ratio, we're going to get that it's equal to D over D plus D1. Now, once again, we have that the average inductor voltage is equal to the average load current, which is equal to VO over R. And then from this waveform here, we can compute the average load current, the average inductor current, I'm sorry, and that's equal to, so if we find this area, we want to take the whole area under this triangle and then multiply that by 1 over t. So the area of this triangle is half times base times height. So we get, if this is I max, then we have that the area of this triangle is equal to half times I max times dt. And then the area of this blue triangle is equal to half times I max times d1t. So if we cancel out the t's, we get the average inductor current is equal to half times I max times d plus d1. So if we plug this in here, we have that these two expressions are equal. So this is the average inductor current. Now, we can find the change in IL. So once again, during the D interval, we have that the inductor voltage is equal to the source voltage minus the output voltage. And we know that we have from the characteristic inductor equation, which during this interval, because the output voltage is constant, we have it linearly increasing. So we can just express this as delta IL over the time interval dt is equal to delta IL is just equal to I max in this case, because the current is starting from 0 and going up to I max, and the time interval is dt. So therefore, we have that I max equals delta IL, and delta IL we had found before is equal to Vs minus Vo over L times the time interval dt. And we know from this equation here, if we substitute that in for Vs, we'll find that this expression equals Vo times d1t over L. So this is the expression for I max. So we're going to plug in this expression for I max into this equation here, and we're going to get that half times I max, so I max plugging this expression in, times d plus d1 is equal to the load current VO over R. So this equation, if we manipulate things around, we'll get a quadratic equation in D1, and that looks like D1 squared plus D times D1 minus 2L over RT equals 0. And if we solve this quadratic equation, we're going to find that the solution is the uh, larger root, and D1 equals negative D plus square root of D squared plus 8L over RT over 2. And we had to choose this root because D1 is positive. The other root would have been negative. So we found this expression for D1. Now, if we want to find the expression for the conversion ratio V out over the source voltage, we can just plug in D1 for um, this value here. So if we plug that in, we get VO over VS equals D over D plus D1. And plugging this in, we get that the voltage conversion ratio equals 2D over D plus square root of D squared plus 8L over RT. So we found the voltage conversion ratio for the buck converter in discontinuous current mode. And one thing to note is that we have the boundary between continuous and discontinuous current happening for D1 equals 1 minus D. And we can see that in the waveform here. We want this D1 value to be less than 1 minus dt. So this is a condition for discontinuous current. As before, we mentioned in our continuous current analysis, another boundary condition happens is for when the minimum inductor current I min equals 0. So these are our conditions for discontinuous current. Now, for this voltage conversion ratio for discontinuous current operation, if, for example, we have some buck converter that we're operating, and say we have some duty cycle D, let's just call this the duty cycle axis, and it goes from a duty cycle of 0 all the way up to 1. And let's call this axis, this vertical axis, the voltage conversion ratio V out over Vs. And basically for a buck converter, we have in continuous mode, we have V out over Vs equals D. So this is just a linear slope. Um, and we have that for continuous operation, it's just a straight line. So whatever linear increment we give in the duty cycle, we get a linear increment in the voltage conversion ratio. However, say for example, we have some converter, we've chosen the inductor value and switching frequency such that for certain portions of the duty cycle, we're in discontinuous current mode. In that case, using this equation, we will actually find that, for example, the discontinuous current will give a voltage conversion ratio that is larger than that of the continuous mode. So for this example of a converter, we have discontinuous current operation here from um, from a duty cycle of 0 up to some duty cycle. Let's just call this duty cycle uh, dx. And then we have continuous operation from dx all the way up to 1. And what this shows is that in discontinuous current mode operation, for a given duty cycle, we have the voltage conversion ratio for discontinuous mode is larger than that for the same duty cycle for continuous mode. So overall, this is the analysis of the buck converter for both the continuous current mode as well as the discontinuous current mode. And I hope you found this video helpful in understanding buck converters as well as an introduction to switch mode converters in general. And if you found this video helpful, please do give this video a thumbs up as well as subscribe to my channel. Thank you very much for your time and watching, and I hope you have a good day. Thank you.